Morning to one and all. My name is Ciso with roll number 4J8 and I am from ECE section. Today my topic is about let you through a brief walk through noise and coming to the introduction. As the title suggests, I am inviting the reader to take a brief walk with me and discuss the interesting subject of microwave noise. My goal is to provide some highlights on the subject from its basic pillars based on physics to the latest engineering publications. A solid understanding of noise cannot but stand on the shoulders of the physicists who have continually been looking at overcoming the limitations of any theoretical model to explain nature. Names like Brown, Einstein, and Nyquist must be mentioned before focusing on the applications of those ideas, which started more than 100 years ago. How do you describe noise when considering microwave circuits? How do you characterize noise in microwave circuits nowadays? And coming to the physics background, noise was a subject of research well defined before the man made electromagnetic waves traveled across the Atlantic. The description of random motion is attributed to Robert Brown, a Scottish botanist with a keen interest in using microscopes. His observations from a particular plant in the given figure, published in 1828, became famous. This plant was Clarkia pulsella, of which the grains of pollen taken from anthem full grown, but before bursting were filled with particles or granules of usually large size varying nearly 1 by 4,000 to about 1 by 5,000 of an inch in length and of a figure between cylindrical and oblong, perhaps slightly flattened and having rounded and equal extremities. The adoption of electrical communication at the dawn of the 20th century brought the issue of noise to the forefront of science and engineering, as it became obvious that signals are degraded as they travel from a transmitter to a receiver. Through the gift of scientific lenses and time travel, it is easy to say now that research in black body radiation during the early 1900s was essential to understanding noise. A black body is defined as an idealized, perfectly opaque material that absorbs all of the incident radiation at all frequencies, if reflecting none. Rayleigh and Jeans could determine that the power density exchanged by a black body at temperature T and unit bandwidth B of 1 Hz around its center frequency F 0 is P is equal to K into T into W Hertz. This familiar expression carries two important consequences. It fits measured data well as long as the frequency under consideration is well below the optical region at room temperature. The total energy in bandwidth P goes to plus 3 as the bandwidth increases. The second issue came to be known as the ultraviolet catastrophe because one fails as frequencies approach the optical domain. Indeed, this did not make sense. Something was obviously incorrect in scientific understanding of the problem. Noise formalism. Another piece of the noise puzzle must be introduced before talking about noise and techniques for its measurement. How is noise handled when analyzing an electrical circuit? The basic answer came from Nyquist in 1928 when he demonstrated with arguments very similar to those used by Rayleigh, Jeans, and Planck that the noise spectral power a resistor can exchange under thermodynamic equilibrium is kT. The result is important because it provides the link between black body radiation and a resistor. As figure 2 illustrates, a resistor can effectively model a black body by associating its temperature to an equivalent value of TEQ. Furthermore, the spectral power associated with a black body implies as an exchange of power between the black body and the external environment. The power exchange is maximum power the body can exchange in equivalent words. It is the available power. associated with the equivalent resistor at the ambient temperature it happens to be. What makes a good receiver? Before talking about noise measurement techniques, we need to understand what can be measured. The main goal of any RF circuit, broadly speaking, is to support the transmission and recovery of information from a transmitter to a receiver. The information is appropriately carried by a signal S of t through a channel, be that a cable, an optical fiber, or free space. The receiver, however, will also pick up an additional unwanted signal N of t that shows up as crackling noise out of your low-tech radio receiver when no signal of interest S of t is present. We will call the unwanted signal noise and assume that the receiver processes both S of t and N of t linearly because the signals either alone or combined don't push the receiver into saturation. The nature of the signal N of t will determine the character of this noise. In this context, we are a little fuzzy, and the implication is that N of t is effectively white noise rather than a powerful interfering signal booming through your speakers. The ratio of the power S associated with signal S of t with the power N associated with the noise N of t is the signal to noise ratio, typically referred to as SNR. The higher this ratio, the smaller the noise power compared to the signal of interest power. In other words, an overwhelming strength of S of t compared to the noise strength will make its recovery by the receiver easier. The issue is that every subcomponent of the receiver, such as the amplifiers, mixers, and filters, will also introduce their own noise and conspire to make the recovery of S of t more challenging. Why? Because the SNR found at the output of each component is reduced by the amount of noise power that the component is delivering to the next stage. The higher the noise, the lower the SNR, and the more challenging the recovery of the information that the signal is carrying. This is particularly true when the signal of interest has just been detected by the antenna and input into the first stage at the receiver chain, like the one illustrated in the figure 4. Indeed, any noise added by the first couple of stages of the receiver chain may significantly affect the output SNR. Once the signal has reached the following stages, the noise added should be essentially negligible compared to the signal of interest S of t. Maintaining a sufficiently large SNR is a key feature of any receiver and a fundamental challenge for RF designers at both the system and circuit levels. What are the options to accomplish this goal? One can amplify the input signal, make sure that each subcomponent introduces as little noise as possible, or do a combination of the two approaches. Of course, the devil is in the details. The receiver chain design. The LNA must be the first stage of the chain to achieve the good noise performance. LO is nothing but the oscillator, local oscillator. The LNA attenuator and the local oscillator filter amplifier RF output combined gives the receiver chain design, which is the most important. Now, how can we measure the noise? Measuring microwave noise. A microwave noise figure meter measures the noise power of the device under the test, also called as DUT. Over frequency and typically displays its noise figure. The instrument must control a noise source connected at the input of the DUT to deliver NI and make the measurement and the proper calculations. An example of a modern noise figure meter is seen in figure 5. At its core, it consists of a receiver tuned at frequency F0 that detects the noise power N0 delivered by the DUT within a known bandwidth P. The receiver makes use of 11 to calculate frequency from the measurement of N0 after de-embedding the noise contribution of the receiver itself. Thank you.